Good morning, everyone. So, welcome to class number 3 of transport phenomena in mesoscopic and nanoscopic systems. So, first of all, there has to be a correction in the problem statement which I discussed at the end of the last class in hurry. So, this assignment is also show the average, not energy position etc., but average probability density of beta xt, that is beta star xt beta xt or mod of beta xt square is a function of time. So this should be the problem statement. Okay, so today we will first discuss about eigen functions and eigen values, and as it seems that for a beginner who has zero knowledge in quantum mechanics would generally find it confusing to understand eigen functions and eigen values, and so I will just state some points for which you might have confusions so that it is clearer for you to understand. Okay, so let us say that we have an operator in quantum mechanics which is the operator q, and q, as I said, is generally a function of the position operator and the momentum operator. Okay, now let us say that q acts on a wave function, or q acts on a function which we call as gamma. Okay, or gamma x, because we are dealing with mainly the spatial functions now. We are not putting in that time factor because we already know that it is an exponentially varying, not exponentially varying, but it is of the form of exponential minus I e by h bar t. Okay, so we will not take this factor into account from now on, and we will only deal with the spatial wave function part. Okay, so let us say qxp operates on a wave function gamma x, then if it produces a number q times gamma x, then so if this operator q acts on a function gamma x and it returns this number q times gamma x, then gamma x is said to be the eigenfunction of the operator q and of the operator q, and q is said to be the eigenvalue corresponding to the eigenfunction. Okay, now note that if q would act on any arbitrary function, let us say beta x, q would act on any arbitrary function beta x, then it would produce maybe some constant c times another function, let us say alpha x. Okay, in this case beta is not the eigenfunction of this operator q. Please understand this thing very carefully. that q is just an operator in quantum mechanics. It might be the position operator, it might be the momentum operator, it might be the energy operator, it might be let us say the kinetic energy operator or anything. Q is just an operator and q might act on any function. Okay, if q acts on any function, in that case it can produce a constant number times another function, or it can actually produce anything. It can produce constant number times an arbitrary function, or it can produce, let us say, a summation of other terms, so c d times lambda x, and plus it might produce many other terms actually. Okay, so it is not guaranteed that the operator q would actually act on any function to give a function of this form or a solution of this form. Okay, it is not guaranteed. It is only when q acts on its eigenfunction, only then we have this form. So for this form to be valid, the operator q should act on its corresponding eigenfunctions. If q acts on any arbitrary function, then this equation would not come. Okay, or if q acts on any arbitrary function, then we would not get a number multiplied by that function itself. That is happening here. Okay, this is happening, that q is acting on this function and it is producing this number q multiplied by the function itself, because this gamma is basically an eigenfunction of this operator q. Okay, so an eigenfunction would produce an eigenvalue only when it is operated by its corresponding operator, or let us say an operator acting on a function would produce an eigenvalue when that function is the eigenfunction of the operator itself. Okay, so an operator acting on a function would produce an eigenvalue only when the operator is the only when the function is an eigenfunction of the corresponding operator. Okay, so if so eigenfunctions are nothing but the solutions of this equation So eigenfunction gamma x are nothing but the solution for gamma x for this kind of equations. Okay. Now note that q here, this small q is just a number. This gamma x is a function and q is basically an operator. Okay. Now in quantum mechanics, because we are generally talking about operators corresponding to observables, so observable means some quantity which we can measure. Okay, for example, the position, the momentum, the energy, these are all observables. Okay, although it's very difficult to actually measure momentum in an experiment, but hypothetically we can always measure, but we cannot measure the wave function. Okay, so please note the difference, that wave function is basically a hypothetical concept that we have actually taken into account to unveil or to explain what is happening in the system, but we cannot measure a wave function. Okay, so wave function is not an observable. Okay, so wave function basically is not an observable. So it is just a hypothetical theoretical construct that we have taken into account to actually explain what is happening in the system, but we cannot measure a wave function. What we can measure is either the probability density of the electron to occupy a certain position, or the momentum, or the energy. So these are basically observable, something which we can measure. Okay, so momentum, energy, position, etc. These are basically observables. Okay, now this wave function is not an observable, and as I said that it cannot be measured, and it is very clear from the fact that the wave function is actually an imaginary complex number. For example, if I express this wave function gamma xt, let us say, let me go to another page. So if I express a wave function as gamma xt as exponential minus ikx, which is the simplest form, exponential minus ie by h bar t. We'll just ignore, not write the minus here, we'll just do with plus for a wave propagating in the positive direction. Okay. So if we express the wave in this form, see that it is actually a complex number, because this part is also complex and this part is also complex. So it has a real part and an imaginary part. And as we already know that we cannot really measure imaginary part, or imaginary part does not actually exist. Okay, we only use imaginary numbers for ease of calculations. They do not actually exist in nature. Okay, so and it is clear that a wave function does not actually exist in nature, but it is just a hypothetical concept that is used to explain the principles of quantum mechanics. Of course, the electron wave actually exists. The electron wave would exist, the probability would exist, charge density would actually exist, but the wave function is actually a hypothetical concept. Okay. So when we actually try to deduce the electron wave from this expression, we actually take the real part. Okay, so the real part of this is just so the real part of this function is just the cosine term, so cos of kx minus e by h bar t. So this is the electron wave actually. Okay, although it cannot be again it cannot be measured in an experiment, although, but this is actually something which has a physical meaning. Okay, but the wave function itself does not really have much physical essence to it. Okay, similarly this position, energy and momentum, these are observable, and observables cannot be imaginary number. For example, if I measure the momentum of an electron, the momentum cannot be an imaginary number. Or if I measure the position of an electron, the position cannot be imaginary number. If I can measure, if I would like to measure the energy of an electron, the energy cannot be imaginary number. So all these things, energy, momentum, position, etc., these are basically observables, and hence this has to be real numbers. Okay, and since this should always be real numbers, therefore the operator corresponding to these observables are Hermitian operators. Okay, so what is the condition of a Hermitian operator? So we'll quickly just go through it. If we find time later, we'll come back to this, but right now just let us just know the condition. If Q is a Hermitian operator, then integral minus infinity to plus infinity psi x star, actually psi x star with the operator q acting on psi x dx should be equal to q psi x star psi x dx. So this is the condition of a Hermitian operator. In other words, the average value. So this is basically, as we discussed earlier, that this is the average value of the operator q for the wave function psi x. Okay, so in other words, the average value of the operator q is equal to the average value of the operator q star. Now a Hermitian operator always have real eigenvalues, and the next point is the eigenfunctions of a Hermitian operator always satisfy always form a complete orthogonal set. Again, we will come back to it later if we can find time, but for the time being, what does it mean when we say a complete orthogonal set? I will just explain to you in a very simple language so that it's not much difficult to understand. Instead of going to a very mathematical language or bookish language, I will try to explain in very simple terms. So let us say that we have this operator q which acts on this wave function psi x to produce a number which is q multiplied by this wave function psi x itself. So if I solve this equation, I would get a set of wave functions psi x, okay, and a set of eigenvalues for this operator q. Now let us say that two wave functions, if psi 1x psi 2x and if psi 1x and psi 2x are solutions of the operator q, and psi 1x not equal to psi 2x, then integral of psi 1x star psi 2x dx equal to integral of minus infinity to plus infinity psi 2x star psi 1x dx should be equal to 0. So this is what I mean by orthogonal states. Okay, so this condition is termed as orthogonality. Okay, so when we discussed in the last page, I said that it basically forms a complete orthogonal set. Okay, complete orthogonal. So I have already explained what an orthogonal set is. Now let us discuss this term complete. So a complete set of states or a complete set of functions means that any other functions in the system that satisfies the suitable I should not say in the system, but in the space. Actually it is a Hilbert space, but I will not go into those complicated terms and explain what a Hilbert space is. I am just trying to keep things simple here. Okay, so any other functions in the space that satisfy suitable boundary conditions can be expressed as a weighted sum of can be expressed as a weighted sum of the set. Okay, so for example, for any function with a period t. So if we talk about Fourier series, I am again not defining Fourier series, but I am just trying to explain what this complete set is basically. So any function with period t can be expressed as a weighted sum of sinusoidal components with period t, 2t, 3t, etc. So this complete set of sinusoidal components with period t, 2t, 3t, 4t up to infinity forms a complete set for any function with a period t. Okay, or forms a complete basis for any function with a period t, because any function in space, here the term in space means that with a period t. Okay, so any function with a period t or any function in the space which has a period t can be expressed as a weighted sum of sinusoidal components with period t, 2t, 3t, etc. So the sinusoidal components, the set of sinusoidal components with period of integer multiples of t form a complete set or a complete basis for any function with time period t. Okay, So Fourier series, as you already know, that the basis is a complete orthonormal basis. Okay, the basis in Fourier series is basically a complete and orthonormal basis. So here I use the term orthonormal instead of orthogonal because we already know that the components, the sinusoidal components in a Fourier series are basically normalized, that is their integral over one time period is basically set to 1. Okay. So in this case I have not yet used the term orthonormal here. I have used the term orthogonal because we have not yet gone up to there, but indeed here also we need to actually normalize the eigenstate. So we will go there shortly, that why we need to actually normalize the eigenstates, and the very crude reason is that the square of the mod of the eigenstates basically define the probability density. Okay, so we'll go to there. Okay, so the eigenfunctions of a Hermitian operator always form a complete orthogonal set. Okay, and this set can be normalized to form a complete orthonormal basis set. Okay, so basis set basically denote the components which are used to denote any function in that space. For example, in real space, the bases are basically the unit vectors along the x, y and z directions, because any vector in real space can be broken down in terms of those component vectors. Similarly, in the Fourier space, or in case of any function with a time period t, that function can be broken down in terms of sinusoidal components with time period 2 t, 2t, 3t, etc. So those sinusoidal components basically form the basis set. So the sinusoidal components with period t, 2t, 3t, etc., these basically form the basis set of any function with a time period t, because any function with a time period t can be expressed in terms of this sinusoidal component with period t, 2t, 3t, etc. Okay, so I hope you are getting the drift, that the eigenfunctions basically form the spectrum of the entire system, or the spectrum of any wave function that can exist within the system and that satisfies the suitable boundary conditions. Okay, so eigenfunctions, the importance of eigenfunctions lies in the fact that they form the spectrum of your system. Any wave function that satisfies the suitable boundary conditions can be broken down in terms of eigenfunctions. Okay, and whenever we measure a parameter of the system, for example, whenever we measure the momentum of the system would collapse to one of the eigen functions of the momentum operator, and we will get the eigenvalue corresponding to the momentum operator. Of course, there are many eigenfunctions of momentum. There are many eigenvalues corresponding to those eigenfunctions of momentum. So whenever we measure the momentum of a system, the system might collapse to any one of those eigenstates, and we will get the momentum corresponding to that eigenstate only on measurement. Now if I do measurement 10 times, then 10 times I might get different momentum measurement, but each time when I measure the momentum, I would get a momentum corresponding to an eigenstate of the momentum operator. Okay, so I hope I have made the point clear about eigenstate and eigenvalues. Okay, so let us proceed further. But before proceeding, I again repeat that eigenstates are basically basis component that can be used to express any wave function that exists within the system with suitable boundary conditions or with a given set of boundary conditions. Okay, so you can compare eigenstate with the Fourier components or with the sinusoidal components that form the basis function in Fourier space. Okay. Now we will go to another very important concept in quantum mechanics, which is known as commutation. And note that whatever we are covering in this course is absolutely essential to actually understand quantum transport, and whatever is not required to understand quantum transport, we are completely omitting those parts. Okay, we are only covering those parts of quantum mechanics that is required to understand quantum transport, and this is the bare minimum of quantum mechanics that you should actually know to understand quantum transport. Okay, so let us now go to another important part. This is known as the canonical commutation relation. Now, in classical mechanics, whenever we multiply two numbers, let us say we are multiplying a number x with a number p, it does not matter in which order we multiply these two numbers. Okay, because if we multiply 3 with 5 and whether we multiply 5 with 3, this is basically going to give me the same result. Okay, so this is a property of all classical functions. This is a property of all classical functions. So I mean, it is very intuitive and it does not require much explanation. And if you remember, in class 8 or class 9, there used to be a very funny thing that we actually learned in physics and maths, and which used to be written in every physics or maths book, is that algebraic numbers have this property AB equal to BA. And actually you used to wonder that why is it even written? Isn't it obvious that any algebraic number basically has this property? So it is written because people actually proved it for numbers, and people also proved something else for operators actually. Okay, so in quantum mechanics, just as I stated that these are not numbers or functions, but these are basically operators. So let us say that I basically multiply this x operator and p operator. Okay, and I subtract from it the reverse thing, that is a multiplication of p operator and x operator. So okay, now if this relation would hold in quantum mechanics, then, or quantum mechanical operators, then this thing would be 0. But let us check if this thing is actually 0 or not. So this combination of x operator and p operator is actually an operator, and this operator has to operate on something, some function. So let us actually operate some wave function with this operator. So let us take a wave function psi x over here, and p operator, as we know, this is equal to minus I h bar del x. So x operator I h bar del x minus I h bar del x times the x operator times psi x. Okay, now note that this is an operator here. So an operator only acts on functions, or an operator only acts on numbers, but an operator cannot really act on another operator. right? An operator has to act on functions, or an operator can act on numbers. Okay, so let us just see what the result is. So the first term, this one gives me the result x operator. So I h bar x operator del psi del x minus I h bar del x. So first the x operator would act on this wave function psi x, and what does this x operator do? So this x operator basically gives us the position of this wave function or this particle psi x. So this x operator is nothing but it basically multiplies x psi x by its position. Okay, so this basically becomes I h bar del psi del x minus I h bar del x of x psi x. Okay, so this operator again acts on this del psi del x to position. So this thing here becomes I h bar x del psi del x minus I h bar psi x minus I h bar x del psi del x. Okay, so this thing and this thing here cancels out, so we have minus I h bar psi x. Okay, so whatever we get now is basically x p minus p x acting on psi x basically gives me minus I h psi x. So this this operator, this is a combination of two different operators, so this is also an operator. So x operator p operator minus p operator x operator is equal to minus I h bar. So how do we express it in a mathematical language? Is third bracket of x operator comma p operator is equal to minus I h bar, and so this expression is basically equal to xp minus p operator x operator. Now what does this signify? Why is this result important? So I mean, there are many practical importance for this equation, and this equation is very important, and I think you have to take my word granted right now, because this is a very basic quantum mechanics, and really it is not possible to stress how much this kind of commutation relation is important. But one of the very basic reason why this relation is important is because this relation basically measures, or this relation basically makes us understand if two operators basically has the same set of eigenstates. Okay, I repeat again that this relation basically tells us if two operators have the same set of eigenstates. If two operators have the same set of eigenstates, if two operators have the same set of eigenstates, two operators, let us say A and B, so A operator and B operator, if they have the same set of eigenstates, then A commutator of A and B is 0. So this is known as the commutator. Okay, it basically commutes the two operators. Okay. Now what this relation here proves is that this x operator and p operator do not have the same set of eigenstates. Now this relation is this thing is a bit complicated to prove that two operators have the same set of eigenstates if this a operator and b operator are commuting. Okay, are commuting means that their commutator is basically 0. But let me give you a very simple and easy explanation. Okay, so let us say two operator a and b are basically acting on some wave function, let us say beta x. Okay, now beta x is neither a wave a beta. Now let us suppose that beta x is neither a eigenstate of the operator a, or beta x is also not an eigenstate of the operator b. So we have two operators here, and beta x is neither an eigenstate of the operator a nor an eigenstate of the operator b. So then let us say I take the basis corresponding to the eigenstate of the operator b only. Okay, so then beta x, because the eigenstate of an operator, of a Hermitian operator, that is, and we are considering a and b to be Hermitian operators, so let me write it here. So what is an Hermitian operator? A Hermitian operator is an operator that whose eigenvalues are real. So we are always talking about observable things we can observe in quantum mechanics. So the eigenvalue of the measurement has to be real, and the eigenstates of a Hermitian operator basically form a complete orthogonal basis. Okay, so since it forms a complete orthogonal basis, this beta x can actually be expanded in terms of the eigenstates of operator a or operator b. Okay, so let us say that operator a and operator b basically have the same state of eigenstates. Okay, so our intention is to prove that if operator a and operator b has the same set of eigenstates, then their commutator is basically 0. This is what we want to prove basically. Okay, so let us say that operator a and operator b has the same set of eigenstates, and we denote that set of eigenstates with the help of say lambda n, let us say n equal to 1, 2, 3, 4, 5, etc. So this is basically our eigenstate of the operator a and the operator b. They both have the same set of eigenstates. Okay, so this beta x can actually be broken down, because this set of eigenstates of operator a or operator b basically forms a complete orthogonal basis. Beta x can therefore be broken down in terms of this complete set. So we have commutator of a b summation over n Cn lambda n x, where Cn is basically constant, and these are third bracket, not the commutator, so I will just omit this. So we now write the complete relation AB minus BA AB minus BA acting on this set Cn lambda n x. Okay, now we have summation over Cn. Cn are constant, A, B operator acting on lambda nx minus so we have another bracket over here, minus b operator with a operator acting on lambda nx. Okay. Now remember that lambda nx are the eigenstates of both the operator a and b. Therefore, we have summation over n Cn operator a. Now this is basically equal to a number times lambda nx. So we call this number as Bn lambda nx minus operator b, and this operator acting on lambda nx is also a number multiplied by lambda nx, because lambda n is basically an eigenstate of this operator a also. So we call this number small a n multiplied by lambda nx. Okay. So again summation over n Cn. Now this operator a would act on this function. Note that this is a number, so this operator a would not act on this number. Okay, operators only act on functions. Okay, so I mean operators in quantum mechanics, that is, only act on functions. So we have this Bn n operator multiplied by lambda nx minus an b operator multiplied by lambda nx equal to summation over n Cn Bn an lambda nx minus an Bn lambda nx. So these two terms cancel each other, and so the net result is 0. So we have proved that if this operator a and b has the same set of eigenstates lambda nx, then their commutator is 0. If their commutator is not 0, then these two operators a and b does not have the same set of eigenstates. Okay, so this relation is mainly to understand that if these two operators commute or not, that is, so whatever we have written here, this basically means that the position operator and the momentum operator does not have the same state of eigen, does not have the same set of eigenstates. Okay. So I do have assignment for you. So your assignment is that prove that the momentum operator, which is basically minus I h bar del x, is a Hermitian operator. Okay, so I have actually done a mistake over here. So this momentum I have written as I h del x, so it should be minus I h del x. So we should have a minus term over here, and we similarly have a plus term over here, because the momentum operator is not I h del x but minus I h del x. Okay, so we should have a minus term over here and a plus term over here, again minus here, plus here. So this commutation relationship is just I h actually, not minus I h. So yeah, so here it is actually plus I h instead of minus. Okay, so prove that this is a Hermitian operator, and before this let me give another question. find out the eigenstates of the momentum operator and argue that they form a complete orthogonal set, and this is number 2, prove that the momentum operator is a Hermitian operator, and number 3 is show that the eigenvalues of the momentum operator are real. Okay, so just as I stated that it has to be real because momentum always has to be a real number, it cannot be an imaginary number. So let us do up to here today. I'll see you all in the next class. Thank you.